This is a correction video for the videos about hybridization. When I was writing the next set of lectures about multiple bonds and how p orbitals needed to be unhybridized and available, I realized that I made a series of mistakes in the lecture videos when I talked about what sorts of atoms could be hybridized and what sorts of atoms couldn't. So you need to go back to your notes and find these 4 places: the place where we defined hybridization, the place right under it where we made the list of the features, and the very bottom of the page on sp2 hybrids and sp hybrids. We're going to make some adjustments and fix those things that we wrote so that they have correct information in them. So when I wrote the definition for hybridization, I wrote that the blending of atomic orbitals on a bonded central atom to make new hybrid orbitals, and we need to cross out the word central in both of these cases, because what I realized when I was talking about multiple bonds for our next lecture is that there is hybridization on terminal atoms as well. Terminal atoms can hybridize too. It's not as important as the central atom, which is why I forgot to talk about it, because usually we're only looking at central atoms that have lots of electron groups attached to them. But I did come up with some circumstances where terminal atoms can hybridize, and 2 of them happen to be in the examples that we talked about. So when we listed an example for sp2 hybridization, we used this COF2 molecule, and we looked at the hybridization for the carbon. We said that the carbon was connected to 3 electron groups, and if it was connected to 3 electron groups, it needed 3 sp2 orbitals to hold those groups in. And in the following lecture, we said that that 4th p orbital that was unhybridized was used to be part of this pi bond. But what I realized was oxygen is also part of the pi bond. It's the other half of the pi bond. So oxygen needs to be sp2 hybridized as well to make sure that it has 1 p orbital left over for that pi bond. So oxygen's 3 electron groups are the carbon and its 2 lone pairs. If we look at the fluorine, fluorine is not part of a double bond, so it doesn't need to have any p orbitals available. So we can say that the fluorines are sp3 hybridized, because each of those fluorines has 1 bond to a carbon and 3 lone pairs to hold on to. So it has 4 electron groups, so we can consider it to be sp3 hybridized. So let's draw the orbital overlap for this again and try and make a slightly more accurate version this time. So carbon is going to be sp2 hybridized. So it's going to have 3 sp2 orbitals in this picture. And then our oxygen is also going to be sp2 hybridized. So it has 1 orbital left over for that pi bond. So it's going to have 1, 2, 3 oxygen sp2 orbitals. And if you like, you can draw the lone pair in as a pair of dots in those 2 orbitals that are holding lone pairs. And for the fluorines, we're going to estimate those are sp3 hybridization, with 3 of those orbitals holding lone pairs. This is an sp3, and this is an sp3, and this is an sp3, and this is an sp3. We don't technically need to draw the others because they're not part of a bond, but we will do it just to make sure that everybody's on the same page here. And our other fluorine will also have 4 sp3 lobes, 3 of them with lone pairs in them. sp3, 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 sp3. So there is now an awful lot more going on in the picture, but the important part is that this oxygen fluorine bond is an overlap between the carbon sp2 and an oxygen sp2. And then each of these carbon-fluorine bonds is an overlap between a carbon sp2 and a fluorine sp3 to make 3 sigma bonds. If we want to be even a little spunky, we can draw in the p orbitals. We know that carbon is going to have a 2p orbital. We can say it's on the y-axis. Fluorine is not part of a double bond, and then the oxygen is also going to have a 2p orbital on the y-axis. And that overlap forms the pi bond. Okay, now let's go and fix our sp picture. So in this picture, we originally hybridized the carbon, and we said carbon has 2 electron groups. So it was sp hybridized, but that leaves it with 2 available p orbitals, 1 for this pi bond and 1 for this pi bond. But oxygen also needs to have p orbitals available for those pi bonds. So we can say that the oxygen is sp2 hybridized because it needs 1 orbital for the sigma bond with the carbon and 1 for each of those lone pairs, with 1 p orbital left over to be part of that pi bond. So let's go ahead and draw the orbitals in our picture. So carbon has 2 sp lobes that are at a 180-degree angle to each other. And then each of the oxygen is going to have 3 sp2 lobes. One of them overlapping with carbon, the other 2 holding its lone pairs. And the same for the oxygen on this side. Hopefully your picture looks slightly more symmetrical than mine. Oh, hold on, we wrote carbon, oxygen. These are oxygens, and this is oxygen. Mistakes happen. Here we go. And since we know about pi bonds now, why not go the extra mile and draw the pi bonds? Because this is a cool molecule. So carbon is going to be used 1 p orbital for the left double bond and 1 p orbital for the right double bond. And those p orbitals are going to be at 90-degree angles to each other. So we'll say for the left one, we'll use p orbitals on the y-axis for carbon and oxygen. That will be one of our pi bonds. And then the other pi bond needs to be on a different axis because the x-axis is taken with the sigma bonds here. This pi bond is on the y-axis. So our other pi bond needs to be on the z-axis, the one that's hard to draw. So we'll draw those extra p orbitals sticking out of the page like this. There's the carbon p orbital on the z-axis and the oxygen p orbital on the z-axis. That's where our second pi bond comes from. This is a sigma bond, and this is a sigma bond. And we've already drawn it in the first picture. So 2 sigma bonds and 2 pi bonds, with one of the pi bonds occurring on one axis and the other set of pi bonds on the perpendicular axis. So I hope this clears up a little bit that misconception that I accidentally introduced about which orbitals are used to form those overlaps. Main idea of the correction, terminal atoms can also experience hybridization. So you can hybridize an atom at the end of a molecule that is part of a double or a triple bond.